Hello, everyone. Nice to meet you. I'm Eunhae, and I'm here with Jihae to share with you our experience moving from on-premise to Kubernetes using Druid operator. The agenda is as follows. NAVER Corporation, where we work, is a global ICT company, providing South Korea's #1 search portal NAVER and its subsidiaries and affiliates provide services, including digital comics platform NAVER Webtoon, group social media platform NAVER Band, Snow Camera app, and metaverse platform Zepeto. We are responsible for building, operating, and serving data pipelines for providing analytics based on content at NAVER. We currently offer an integrated analytics service called Creator Advisor and specialized metrics for it. To provide analytics, we use to aggregate data using Elasticsearch and Spark in CD8. We've been using Druid since 2018. Recently, we've built and operated our pipelines in a Kubernetes. Since 2018, we have been conducting extensive research on Druid and have delivered presentations at Strata in London and NAVER in Korea. Unfortunately, for the Strata presentation, only the slide link is available. But if you are interested, please feel free to visit. Let's move on to the main topic now. For data pipelines, we used to run on-premises CD8 with additional use of Druid. However, as the ecosystem gradually transitioned to a cloud environment, we began to question whether we should continue to use CD8. The migration of Spark processing to Kubernetes using Spark operator was made as a trial. It was successful and positive. So we decided through the migration with the assistance of Druid operator. If we are to deploy Druid in Kubernetes without an operator, it requires tedious jobs. You first have to set up each roles as a deployment or stateful set, and then configure config maps to allow pods to reference configuration files, and also ensure external accessibility. It means you have to do a lot of work to specify so many things one by one. With the magic of Druid operator, you can cut off a significant amount of work. The only thing you have to do is to describe a Druid specification and then submit it to the Kubernetes API server. The Druid operator will take care of the rest of the boring work automatically. After going through many trials and errors, we are currently operating the Druid cluster with the Druid operator in this slide. Last August, version 27, we improved it in visualizations was released. But at the time of our migration, version 25 was the latest version. So Tanuro was integrated into the Helm chart for visualization. The problems and solutions we experienced in the process will be shared by Jie later in this presentation. Now, let's briefly outline the migration process using the Druid operator and then proceed with a demo. First, we begin by installing the Druid operator. The latest version is 1.2.1, but we will proceed with the version we used at the time of migration. If you use Helm, setting and maintaining variables will not be very hard, but you have to be careful. If the Helm release is deleted, the Druid CRD will also be deleted, and all clusters will go down accordingly. To avoid this kind of disaster, we added an annotation to ensure that the CRD is maintained even when Helm is deleted. The Druid spec is also submitted using Helm. We changed it to a Helm chart by referring to the Druid operator's example file. It has advantages like this. In this demo, some settings were overwritten in TinyYAML to ensure smooth operation in the mini Kubernetes environment. In the case of Zookeeper, we will apply tiny cluster YAML that is improved by Druid operator. Engines with badges is applied to ensure access only to authorized users. We'll explain later why we used engines instead of Druid ACL. We linked load balancer to engines and set it up to link to each component through port. You might wonder why we didn't assign ports to coordinators. It's because access is possible through our router proxy. There is no need to assign it. Now we will hold a demo of what we have just talked about under the mini Kubernetes environment. First, we'll start by installing the Druid operator. And then set up Zookeeper. After that, we'll use the Helm chart to install the Druid cluster and the necessary tools. Now we can see the running here. Let's connect to the router UI via port. This time we'll call the broker health check API. Finally, we'll connect to the terminal UI.
I'm Jianam, and today I will share the valuable insights we gained during our transition to Kubernetes environment. In our specific case, we only performed batch data ingestion during the early morning hours. So allocating resources to middle managers during non-ingestion hours was a significant waste. To fix this issue, we used our in-house HPA. The reason why we had to use our in-house HPA was that it supports Prometheus metric. We already connected Druid metric to Prometheus for monitoring, and in-house HPA can use Prometheus metric without any extra setup. This is the metric we used as the criteria for scaling in and out. Druid worker task slot used count. This metric represents how many tasks are active in the middle manager. Worker capacity, it represents the total number of task slots available in the middle manager. Simply put, this metric indicates how busy the middle managers are. So if we set a target metric at 20%, it means that when the metric goes above 20%, scale out, and when it drops below 20%, scale in. Now, you might wonder, why didn't we use the default HPA provided by Kubernetes? Kubernetes HPA supports auto-scaling based on resources like CPU and memory. However, we needed more accurate auto-scaling using Druid metric, which is why we didn't use it. If you plan to apply auto-scaling using Kubernetes HPA, you can simply do it with Druid operator. You can refer to the following link for more information. And in case of you're wondering, if you want to apply auto-scaling using Druid metric, how can you do it without HPA that supports Prometheus metric? You can apply auto-scaling using Prometheus metric by using tools like Prometheus Adapter or CADA. You can refer to the following link for more information about this. After applying auto-scaling, we encountered an error. When performing native ingestion with hash partitioning, there are two critical stages. First, during partial segment generation stage, data is scattered into middle managers based on hash key values. And next, during partial segment merge stage, data partitions are merged based on hash key value. This is where the problem lies. If a middle manager scales in before the partial segment merge process is completed, it can result in an error because there is no data left to merge. So our team added a Presta logic to the middle manager. As a result, it terminates middle manager only if there are no ingestion tasks. We simplified the Presta logic with this flowchart. First, we check if there are any ongoing ingestion tasks with the router. If there are still ongoing tasks, we look back to the beginning. Otherwise, we terminate the middle manager. But if the API request to the router fails, we can request API to the current middle manager. However, before the request, we need to prevent any new ingestion tasks from being assigned to the current middle manager. As a next step, we repeat the first step with the router. We didn't apply auto-scaling to historical or broker. The reason we didn't apply auto-scaling to historicals is that when a historical starts, it has to download data from deep storage, which is a time-consuming process. We decided it would be difficult to handle a sudden increase in traffic even if we scaled out. In case of broker, we haven't faced any issues where broker couldn't manage sudden increase in traffic. But if you are required to apply autoscaling to broker, you can apply autoscaling with Druid operator. After configuring our Druid cluster, we encountered a problem. In the Kubernetes environment, we found that operations took over 100 milliseconds longer compared to on-premise environment. Finding the reason took much time, but the main reason was identified as the built-in basic auth feature provided by Druid. Without Druid ACL, the response time reduced from 138 milliseconds to just 17 milliseconds. So instead of Druid ACL, we used Nginx proxy for basic auth. So if you plan to use Druid ACL, it will be better to conduct performance tests before applying it. Just as a reference, we used version 25 and also set credential iterations value to 1. According to the guide and one of Druid engineer, it was suggested that setting a lower credential iteration value would improve response times, but it was still slower compared to on-premise. We had a problem with our Druid cluster when restarting historicals. Each historical took a long time, about 20 minutes to restart. The reason for the issue was that it took a long time to load data into the memory of the historicals. The process of loading data segments into the historical is as follows. First, download the data from deep storage to the historicals disk. After that, the data is loaded into the historicals memory. The problem was that this loading process had to be repeated every time the pod was restarted, and it was taking too long. As a solution, we increased the number of threads used for loading the segment cache during restart. This config is about that, and we increased this config to 50. As a result, the duration required to load segments during historical restarts was reduced from 20 minutes to only 1 minute. For your reference, the size of the segments that each historical had to load was 1 terabyte. I will explain the important settings for the coordinator dynamic config that I've discovered while monitoring the overall status of the Druid cluster. First, segments keep moving even in a balanced state without any ingestion or specific actions. The reason is Druid relocates segments in batches of max segment to move to more suitable nodes. Segments are moved whenever there's even a slight advantage in terms of entire cluster. However, in our team, we prefer to stop segment movement even in balanced state, so we changed this config to 0. Also, I will explain the two more important settings. The second config will be used in two scenarios. First is when one historical goes down, segments are redistributed. And second is when new segments are ingested, replicas are created. Replication throttle limit config is the concurrency for these two scenarios. If you increase this value, replica creation or redistribution process will be done more quickly. The default value is 10, and we usually don't change it for normal operations. But we may temporarily increase it when needed. And when 2 or more historicals go down, it re-downloads missing data from deep storage. The maximum number of segments that can be downloaded from a single historical is determined by max segments in node loading queue config. We also use the default value of 100. We have added the pod anti-affinity and node selector to make service stable. The pod anti-affinity ensures that pods with the same label are distributed to different nodes. So we applied this setting to prevent pods with the same role from being distributed to the same node. The problem we faced when not applying pod anti-affinity is as follows. Without pod anti-affinity, if node 1 goes down, 2 historical stop which result in partial output if segment replica is only 2. But with pod anti-affinity, each historical pod is in different nodes, so the issue doesn't occur. Next, let's talk about the node selector. Node selector is a configuration that ensures pods are only assigned to node with specific label. We use the node selector to make sure Druid pods don't interfere with nodes assigned for other tasks, like Spark. So, if a pod has the label lore Druid, it will be only assigned to the node with the lore Druid label. Next, let's discuss the disable PVC deletion finalizer option. We encountered an issue where the PVCs mounted on historicals were being deleted when we delete the Druid cluster. When the PVCs mounted on historicals are deleted, it requires a significant amount of time to download the data from deep storage again if we restart the Druid cluster. The reason was within the Druid operator configuration, where this setting had a default value of false. So, simple solution to this issue is changing this setting to true. Finally, I will explain the performance changes and advantages we experienced moving to Kubernetes. We did performance tests by migrating real data and doing tests with the same traffic. The upper graph represents the response times on Kubernetes, while the lower graph shows response times for on-premise. As you can see, there was not a significant difference in response times between the two. One of the advantages we experienced when transitioned to a Kubernetes environment is middle manager autoscaling. This allows us to save resources by reducing their allocation during non-ingestion periods. Above all, what we found most beneficial in Kubernetes was the ability to respond to failures quickly and easily than in on-premise environment. Lastly, it is very easy to change ceph size as our data expanded. Since we store data segments on ceph, increasing the ceph size to accommodate our expanding data storage needs is a simple task. I'm finished with my presentation and thank you for listening until the end.